Hi, everyone. Welcome to Chapter 13, Link Structures. So we're going to look at link structures, and we're looking at how you can implement stacks using link structures. So in this chapter, we're going to talk about using object references as links. I'm not sure if this is something you ever thought of. You know what object references are, but you've never thought of building like chains of objects using object references. We're going to talk about how linked are different from array-based structures, which is primarily what you've used up till now. We're going to talk about how you manage linked lists, and we're going to talk about how you implement stacks using linked lists. So these are all pretty useful things. You're going to use these things a lot. Linked lists you use a lot. They're much better than arrays, for example, for implementing stacks, and for a lot of other use cases. The primary differences being that with arrays, when you allocate it, it's a fixed length, but with a linked list, you can add and remove things dynamically without having to reallocate the array and copy things over. It's actually a much nicer way to do things in a lot of cases. It can be slower in certain situations than using arrays, but these are things we have to think about. All right, so an alternative to array-based implementations are called linked structures. So linked structures use object references to create links between objects. So an object reference variable holds the address of an object, right? So it's like, well, in C++ it would be a pointer, but it holds the address of an object. So a person object, for instance, could contain a reference to another person object. So I could build my class person, and inside of my person class, I could put a reference to another person object. And that person object, of course, would also have a reference to another person object, provided that you set it and it wasn't null. But you could build a chain of these things, a series of these objects that would make what we call a linked list. And so typically with a linked list, you have an initial reference, which is called the front of the list, or sometimes called the head reference, but it's the front of the list, and then the list is terminated. There are actually a lot of different kinds of linked lists, but in this case, the linked list is terminated with a null reference. So the last item in the list has a null reference. You have a reference that points to the first of the list. So in your code, you would have a reference, for example, a person reference allocated somewhere, and it would be the one that points to the first one. The rest of them, you would not have an explicit reference in your code. You wouldn't have a variable in your code that points to that person object. It would be pointed to by a reference that's in another object that's pointed to by the front reference that you have. So you can see that in this example here. We have the front reference. This is a person reference. It references this first person. The first person, internally, this object has another reference. The object itself has a reference to another person, which of course has a reference to another person, and we keep doing that. And the very last object in the list, we set that person reference to be null. So it's the end of the list. We can say it's the end of the list. It's a null terminated list. Is what we usually call this. So we could also form complicated nonlinear structures like this, and we will later in the class. We'll look at graphs and trees and all kinds of different things that you can implement using this idea of linking things together. We're not required just to have, things in a straight line, something super simple. We can have a lot of complicated things. We can have things that point to things that point back to other things. We can do anything with them that we want to do. Basically, anything we can imagine that we can do, then we can do with that. So with linked lists, as you notice, the only variable that you have is the variable that points to the head of the list, right? The front pointer. So you can't just say, okay, I want to find the seventh element in this linked list. It doesn't work that way. There's no indexes built into it. And so the way that you traverse the list is you have to follow the references from one node to the next. So here's a little piece of code. We have a person reference called current, which we set to equal to the first, which is the front, basically the head of the list. And then we say while current not equal to null. Remember, the terminator of our list is that null reference, right? That null reference at the end. So while what we're looking at right now is not null. We're going to print out the current person reference, and that's going to do whatever it does for the person object. And then we're going to say current equals current dot next. So remember, that person object has a reference to another person, and we usually name these things next. Sometimes we have classes where they point backwards, where you can have a pointer, a reference to the object in front of you and a reference to the object behind you, which has some advantages. It's called a doubly linked list, but in that case, we'd have one called next, and we'd have one called prev for previous. But usually we'd say dot next. It's pretty much the standard nomenclature for this for linked lists. So you would say current equals current points next, dot next. And what that would do is it would take the current reference, that person reference, and it would set it equal to the next person. That basically it would set it equal to the object. It would make it point to the object that the next reference in the current object points to. So let's go back and look at this and see what this would look like here. So let's say, for example, we started here and this was called first. So we would say that current equals first, which means current would point to the same thing as front right here, right? It would point to this. And this link, this reference is dot next. So when we say current equals current dot next, current equals current dot next would be the value of this reference. So we would think about current, it would hop over to this next object, right? And then we'd say current equals current dot next, and that would hop over to this object, and then it would hop, hop, hop while current not equal to null. When we got here, current would be equal to null, and our loop would terminate, right? So we would be able to loop over this list and visit all the different nodes in the list. All right. So one thing that we have to think about with linked lists, because remember, we don't have indexes. These things, they just kind of exist out there in memory, and the only reference to them most of the time is another object that's in the list has a reference to them. So we have to be careful that we maintain the integrity of those links and that list, because if we accidentally lose it, then the node will just get deleted, right? I mean, in C or C++, you'd leak memory, but in Java, the garbage collector is going to clean it up for you, but you're going to lose that thing that you thought that you had, right? So if we want to, for example, insert a node at the front of the list, what we do is we first point the new node to the front node and then reassign the front reference. So you would say, let's say we have this thing called node, right? So what we would say, first we would say node.next equals front, right? And that would set the next pointer reference equal to the front reference. Then we would say front equals node. And what that would do that would add the new front would be this node, and this node would point to the old front. The next pointer of the next reference of the new node would point to the old front reference, right? So we add these things in, but we have to do it in the right order, because if we say, let's say we said front equals node, we have no reference to the front of the list anymore, right? If that's the first thing that we said is front equals node, we have no reference to this list anymore. This list is just gone. Like, there's no references to it anymore. It's going to destroy itself. This one will have nothing pointing to it anymore, no references anymore, which means it'll be destroyed, then this one, then this one, and then this one, all the way down to the end. They'll all be destroyed because we'll have lost the only reference to the first reference in that chain. So we have to be careful that we never lose that front reference, that we always maintain the references. If we don't, you're going to get unexpected, or you're going to get null pointers, you're going to have your things crashing, you're going to lose your list, right? So when we delete the first node, what we're going to do is reassign the front reference accordingly. So if the deleted node is needed elsewhere, we first have to reference it before we reassign the front pointer. So in Java, if we say front equals front dot next, right? That is going to set front equal to this. This node, this original front node, will no longer have any references, and it will automatically be destroyed. Okay? So what we have to do if we want to keep this reference is we'd have to say something like temp equals front equals front dot next. And that would save this reference. Otherwise, it's just going to get destroyed because the only thing that points to it right now is front, and it's going to get destroyed. All right? So far when we've done this, we've talked about lists that contain nodes that are self-referential, meaning a person points to a person. And sometimes you do write code like this. Depending on how you're writing your code, you could have code that actually looks like this. You could have body parts that contain body parts like, let's say you're building like a skeleton and you have a root bone, and it would have a list of, well, sorry, I'm thinking in terms of graphics here, and you guys haven't seen any graphics. But let's say you have objects that represent a person, like a person, but you're composed of these objects. So we have like a torso object, and that torso has pointers to other body part objects. So we could have like arm objects, but let's say that they're not arm objects. We just call them body part objects. So we could have a reference, 2 for the arms, and they could be body parts. We could have 2 for the legs, that would be body parts, and the legs could have references to the lower legs or the knees or the feet or whatever. So we could build things like that. But a lot of times what we're going to do is we're going to want to make lists of objects that don't have these references, because really the list and the thing that we're storing in the list are not necessarily related, right? We have a bunch of objects of a certain type, and we want to store them in a container or a collection, whatever you want to call it. And those things, they don't really have to be involved with the list themselves. We can separate out the object and the list that we store the object in. So what we can do with that is we can have a node class that forms the list and holds a reference to the objects being stored. So there's a lot of different, so to think about how this would work, go back to your generics. We would have a generic, and that generic parameter would be the type of the node that we're going to store inside, right? And so you'd have a node class, and the node would have a reference to another node, and then inside of the node, you would have that generic type T. That would be, there'd be a reference to one of those, and then when you instantiated that node class, you would declare a certain type. You'd say, okay, it's a person. It's a node bracket person, close bracket, right? Or angle brackets. And that would mean that the reference inside it would point to a person. Now we have a list, and our list structure is contained in the node class, and we have our person objects, and our person objects are separate and have nothing to do with the list. All right? So there's a lot of different variations on the basic linked list concept. For example, you can create a doubly linked list with next and previous references, and a separate pointer at the to the rear of the list. So then we could have, we can do lots of nice stuff with this. We can go forward and backwards in the list. It makes it a lot easier to add and remove things from the list if it's doubly linked. We can sort a little easier. We can also make these things circular linked lists, so we can have a circle that goes around. So the next pointer of the rear points to the head, and the prev pointer of the front points to the rear. And you could implement different types of data structures with that. There's a lot of things. There are a lot of cases where you do stuff like this, like in operating systems. You have what's called a ring buffer. A ring buffer is, I'm storing data. Let's say I've got a device driver and I'm reading data off the disk and I'm storing it, and I've got a bunch of memory allocated for that. I don't really want to add and delete memory constantly. I just want to keep using it again and again and again. And so I'm going to keep the memory pages in a circularly linked list. And when I'm going to use, page 1, page 2, page 3, page 4, page 5, and I'm going to go back and use page 1 again. So if I put it in a circularly linked list, I can just step through my list and start back over at the beginning, reusing the old the old memory memory buffers, and I don't have to worry about you know, handling cases where I'm at the end of the list or anything like this. I can just keep going in circles. So there are cases where you want to use different types of linked lists, and there, like I said, like they say here, there are many different types of linked lists. That's the end of this video, and we'll be back in a minute.